All right, in this lesson, we're going to be talking about the atomic structure and electron configurations of different elements. In order to do that, we need to back up a little bit and talk a bit more about the model of the atom and some of the history behind it. So, if you recall from last year, we talked a bit about spectra. So with a continuous spectrum, this is like what we see when we look at pure white light. We see this complete rainbow. It contains all of the wavelengths of visible light, so all the light that we can see with the human eye. And you can see this visible spectrum here goes from about 400 nanometers to about 750 nanometers, and it's the colors of the rainbow. What scientists noticed is that not all elements, when burned, produced this continuous spectrum. Instead, they produced a line spectrum. This meant that there were only a few lines of light that corresponded to a certain wavelength. So, like this picture here shows, sodium just had these two yellow lines. Helium had, a few more, but just a few lines, not this continuous spectrum like we saw here. So we can see this when an element or a compound gains energy, which causes those electrons to become excited. And then those electrons, they can't stay excited forever, so they start dropping back down to their original ground states, and that produces light. And each element will have a unique spectrum that it produces because the electrons within that element are at different energy levels and there's different amounts of electrons. So what this discovery meant to scientists at the time was that there were only certain energies that are allowed for an electron. They can't be anywhere in space. They can only be in certain energy levels. So Niels Bohr was the one who was really making a lot of progress working on this. So in 1913, after studying the spectra and looking at Rutherford's model of the atom, he created what we call the Bohr model, which was the first quantum model of a hydrogen atom. So you can see that here. You've got your nucleus in the center, just like the Rutherford's model, and the electron orbiting around it. However, in Rutherford's model, Rutherford said that that electron could be anywhere. Bohr said that it could only be in certain energy levels. So he created these orbits, these tracks that the electron could be on, kind of like the planets orbiting the sun. So you've got your electron here in energy level 1, n equals 1. It could also get excited if we added heat or electricity or something to this next energy level, and there could be more energy levels past that. So the idea behind the Bohr model was that there's attraction between the electrons and the nucleus, obviously from their opposite charges. We knew that from the Rutherford model as well, that electrons are negative and the nucleus is a small condensed positive charge, and that has not changed. However, Rutherford was able to kind of look at Coulomb's law, which gives us more specifically this force of attraction based on how far away that electron is from the nucleus. So F here is the force of attraction. K is just some constant. These Q's are the charges, so the charge of a proton and the charge of an electron, divided by the distance between the particles squared. What we really need to know with Coulomb's law is that force is inversely related to distance. So force is charge over distance, and force and distance are inversely related. So the closer that electron is to the nucleus, the stronger the force of attraction will be. The Bohr model was unique compared to the Rutherford model and other models that had existed at this time because he said that the electrons could only move in these fixed circular orbits around the nucleus. And this came from that idea of the line spectra that each element produces. So since only certain energies could be allowed, then the electron must be a fixed distance from the nucleus. We call that a quantized energy level. Quantized means it's just a certain amount of energy. We can move that electron. If we add energy, it can move to a higher energy level, which makes it further from the nucleus. If we take away energy, it can move to a lower energy level, closer to the nucleus. But it has to be in one of those energy levels. It can never be in between. So the electrons that are closest to the nucleus, as we saw from Coulomb's law, experience the greatest force of attraction for the nucleus. And the ones that are further away experience less of a force of attraction. However, the more electrons we have in this atom, the less attraction those outer electrons will feel. We call this the shielding effect. So the electrons that are far away from the nucleus are shielded by the inner electrons, the closer electrons. This is because electrons are all negatively charged, and so they repel against each other. So the amount of repulsion against those outer electrons is greater, and it kind of weakens that attraction from the positive nucleus. Example 1 asks us to calculate the energy required to excite the hydrogen electron from the level n equals 1 to n equals 2. We also want to find the wavelength of light that must be absorbed by this atom in its ground state to reach this excited state. So I've listed out the equations that we'll need. The first one here allows us to calculate the energy when we're looking at the different levels that the electron is in. And then this one will allow us to calculate the wavelength once we know the energy. So first we need to find delta E. And we know that the electron is ending up at level n equals 2. So this is n final. So that would be 2 squared. And n initial was the level n equals 1. So we basically just plug this in to solve for it. 1 over 2 squared is 1/4 minus 1 over 1 squared, which is 1. So we're going to end up with this constant times negative 0.75. And so the energy required is 1.63 times 10 to the negative 18th joules. So then to find the wavelength, we need to plug this into this equation. So I'm going to plug that in. H is Planck's constant, which is 6.6261 times 10 to the negative 34th. C is the speed of light. And lambda is our wavelength. So we can multiply lambda to both sides to get it out of the bottom. And then divide both sides by our energy. And then we can just punch these in. And we get 1.22 times 10 to the negative 1, 2, 3, -7 meters. So that is the wavelength of light that is needed to move our electron from energy level 1 to energy level 2. Example 2 asks us to calculate the energy required to remove an electron from the hydrogen atom in its ground state. So in the ground state, the electron starts at n equals 1. To remove it, it means we're taking the electron away completely. And so to say that in our equation, we're going to put in infinity for our n final. So that is just like it's completely removed from the atom. It's not in any energy level anymore. We don't use 0 because 0 would represent the nucleus. So, because the smaller the number gets, the closer it gets to the nucleus. So we're going to use the same equation again. This time n final will be infinity and n initial will be 1. So we're going to plug those in. One over infinity is basically 0, right? Because it's just gonna, oops, that's multiplying. It's approaching 0. So this basically winds up to be 0 minus 1, which is -1. So our energy here is going to be this number times -1, which just makes it positive. And there we have it. So Bohr's model was great for the hydrogen atom. It worked perfectly, the numbers lined up and everything. But the trouble was Bohr didn't take into account several things, including that shielding effect. And so his model was not able to be used for any other atoms. So the equations that he used to predict what energy each electron would be at only worked for elements with one electron, which the only element with one electron is hydrogen. And that was due in part to the shielding effect and in part to the fact that he was trying to predict exactly where an electron was at a given time. We also found that we had this new thing called photoelectron spectroscopy, which showed that there are actually subshells within each shell. So each energy level has multiple sub-energy levels within it. And Bohr was not able to predict that. He thought that each energy level was just singular. And so what happened after Bohr's model was found to have these problems is scientists started to develop the quantum mechanical model. So Schrodinger was one of the first kind of to put a piece of this puzzle together. The quantum mechanical model involved a lot of different scientists from many different disciplines kind of piecing it together over time. So Schrodinger created a model where an electron is assumed to behave like a standing wave. And a standing wave is a stationary wave. So an example would be a guitar string where, it's not actually like the string is not actually moving from one place to another. It's just vibrating. So here is a video of a standing wave. So Schrodinger created an equation to describe where the electron would be. This is called a wave function, and it describes what we call an orbital in this new model. An orbital is an area around the nucleus that has a high probability of containing an electron. So it's just the most likely place around the nucleus where the electrons will be found. This is Schrodinger's equation. We're not actually going to be solving anything with Schrodinger's equation. It's actually very complicated, even though it looks really simple. But just know that he created this equation to describe where the highest probability of electrons would be. Another piece of the puzzle was the Heisenberg uncertainty principle. So this principle basically says that we can never know the location and the speed of a particle that's moving at any given time. So we can't know both of those things with certainty. The more we know about the location of an electron, the less we know about its speed. And the more we know about the speed, the less we know about the location. Whenever we try to measure one of those things, it fundamentally alters the other one in some way. So if we can't know the exact location and speed of an electron, we can't just assume that it has this circular orbit, which is what Bohr was assuming. And so this was really the big thing that proved the Bohr model to be incorrect. Bohr had come up with a lot of good pieces that are still used in the quantum mechanical model, but because he was trying to say exactly where the electron is and what its energy is, it can't actually be used. So in the quantum mechanical model, the electrons do not follow a specific orbital or orbit. Instead, we have the wave function, or the orbital, which describes where the electron could possibly be around the nucleus and just the most likely positions for it to be in. So the possible wave functions are just all of our possible orbitals. So we have our different energy levels, like 1, 2, 3, 4, 5, and then the different orbital names, which are the shapes S, P, D, and F. When we take the square of the wave function, that gives us the probability of finding an electron near a certain point in space. However, we still can't know exactly when that electron will be there, how it gets there, and it's still just a probability. It's not a certainty because of that Heisenberg uncertainty principle. So to show where the electrons will most likely be, we use what's called a probability distribution. We also call this electron density. So you can see in this diagram here, the darker shaded areas are where the electron will most likely be, and the lighter it gets, the less likely it is to find the electron in that location. So you can see if the nucleus was at the center of this, that is where the electron wants to spend most of its time, is closest to the nucleus. So the wave function is just an orbital. We consider it to be the space the electron will occupy 90% of the time. We can't say it with any more certainty than that, just based on the calculations that we can do. But what's also important to know is that this is just a concept. It's just a probability. It's not something physical. There aren't these shells or balloons or whatever within an atom. These are just things, like these drawings are just shapes that are created from the math that we do that show where the electron will most likely be. So we have 4 different quantum numbers in the quantum mechanical model. The first is called the principal quantum number. It's represented with the letter N, and that's the same one that was in the Bohr model that tells us which energy level the electron is in. So the principal quantum number can have values that are positive whole numbers, and it does not include 0. So it could be 1, 2, 3, 4, and on up. So this is related to the size of the orbital and the energy of it. So the bigger the number, the larger the orbital is. And so that electron will spend more time further away from the nucleus. It'll also have more energy because it requires the electron to have more energy in order to be further away from the nucleus. The second quantum number is called the angular momentum quantum number. The symbol for this one is the letter L. L can be anything from 0 to 1 less than whatever n is. So if n is 3, L could be 0 to 2, but it does have to be a whole number. So these are related to the shapes of the orbital, and each shape is assigned a letter. So when L equals 0, then it's an s orbital, which is a sphere. When L equals 1, that is a p orbital, and that's our peanut. When L equals 2, that becomes a d orbital, which is the double peanut. And when L equals 3, that's the f orbital, which is, we called it the flower last year, but it would have 6 lobes. Like this one has 4, it would have 6. The third quantum number is the magnetic quantum number. This is M with a subscript of L. The magnetic quantum number can be anything between negative L and positive L. Again, it has to be whole numbers. And this relates to the spatial orientation of the orbital. So if L equals 1, then ML could be -1, 0, or +1. And that tells us how many different ways that orbital can be located in space. So when L equals 1, it's a p orbital. And there are 3 possible values for ML, which was -1, 0, and 1. And we see that there's 3 ways for the p orbital to be arranged on this XYZ axis. The fourth quantum number is the spin quantum number. This is M with a subscript of S. It can only be one of 2 things. It could be +1/2 or -1/2. And it tells us the direction the electron is spinning. Now, we can't know exactly which direction the electron is spinning, clockwise or counterclockwise. So we just assign it a number. And we know that any electrons that are in the same orbital must be spinning in opposite directions. So one must be going clockwise and one must be going counterclockwise. For the energy of the orbitals, the size of that shape increases every time we go up in energy level. So for the s orbital, when n equals 1, we have a sphere. When n equals 2, we have a larger sphere. And when n equals 3, we have an even larger sphere. So the shape doesn't change if we're looking at that type of orbital. But as the energy level increases, then our shape will get larger. The p orbital has to start at 2. There cannot be 1p. This is because the quantum number cannot be equal to n. The d orbital starts at 3d. We have 5 different ways that the d orbital can be represented in space. The f orbital starts at 4f, and we have all of these different ways that the f orbital can be arranged in space. And as you can see, the bigger these orbitals get, the weirder their orientations become. All right, so with the electrons in these orbitals, in these quantum numbers, typically they will occupy the lowest possible energy state, which we call the ground state. But if we add energy to the atom through heat or electricity, then the electron moves to an excited state. That means it'll be in a higher energy orbital. That means it'll be further from the nucleus. So one thing that governs the electrons in these orbitals is the Pauli exclusion principle, which says that in an atom, you can never have two electrons with the same four quantum numbers. It's just impossible. That would mean it's the same electron. And so what this means is if the two electrons are in the same energy level, the same shape, and the same orientation, then they must be spinning in opposite directions. So polyelectronic atoms is just like a big fancy word for atoms with more than one electron. This is what Bohr was not considering when he created the Bohr model. And they make everything a lot more complicated because you have a lot more to consider. So first we have to consider the energy of the electrons as they move around the nucleus, which was already being considered when there was only one electron. We also have to consider the potential energy of attraction between the nucleus and the electrons. Again, that was also being considered with one electron. The main thing that's different here is this potential energy of repulsion between two electrons, or the shielding effect. And so we get a much more complicated picture when we have more than one electron in the atom. So we can represent polyelectronic atoms using the quantum mechanical model. We couldn't do that with the Bohr model. However, we can't solve Schrodinger's equation exactly because of those repulsions. So we make this assumption that the electron is moving in this field of charge, and this charge is a net result from the nuclear attraction, the positive attraction, and then the average repulsion of the other electrons. It's impossible to know exactly what repulsions that electron will be feeling because all of those electrons are moving constantly. And so we can't know exactly what repulsions it will be feeling. So for example, sodium has 11 electrons. If we're looking at its outermost electron, the one that's furthest away from the nucleus, it feels a force of attraction from the protons in the nucleus, but it also feels a force of repulsion from the 10 other electrons. And so the net result is that that electron is less strongly attracted to the nucleus than any of the other electrons in the atom. So this is, again, what we call the shielding effect, when those other electrons repel the electrons at the outsides. And so the ones that are the outermost electrons in any atom will always feel less strongly attracted to the nucleus. Whenever we have multiple electrons in an atom, the energies of the orbitals for our principal quantum number, n, will increase in this order. So the s orbital will always be the least amount of energy, followed by p, then d, then f, if these are all the same energy level. So like 4s is always less energy than 4p, which is less than 4d, which is less than 4f. Another rule that governs the electrons in these orbitals is the Aufbau Principle. So the Aufbau Principle says that as protons are added one by one to the nucleus, which creates different elements, then electrons are also added one by one. So for each proton, we should have one electron in a neutral atom. Another rule is Hund's rule. So the lowest energy for an atom is one with the maximum number of unpaired electrons. So the electrons do not want to pair up unless they have to. So if we can keep them all singular in their orbitals, that will be the lowest energy possible. So to kind of summarize these rules, the Aufbau Principle says that the electrons will occupy the lowest energy orbitals first. So they start out at n equals 1. Hund's rule says the electrons will not pair in their orbitals. They'll not pair up until every orbital has one electron in that shape and energy level. And then the Pauli exclusion principle says that no two electrons can have all four of the same quantum numbers. A couple of additional rules about electrons filling the orbitals. So the n plus 1 s orbital always fills before the nd orbital. So for example, 4s fills before 3d. 5s fills before 4d. So you should remember this from doing electron configurations. Once we get to lanthanum, we have the lanthanides, which is the 4f orbital. And after actinum, we have the actinides, which is the 5f orbital. And then when we're talking about valence electrons, S and P are the only ones that can be valence. D and F are not. So remember, valence are the ones that participate in things like ionic bonding, covalent bonding. They're the ones that can be gained and lost. So those can only be S and P electrons. D and F will always be core electrons. In example 3, we're asked to write expanded and condensed electron configurations for a variety of different atoms. So just to kind of review, we have these different sections on the periodic table that we can use in order to do the electron configurations. So this first section here represents the s orbital. This block here is P. In the middle, we have D. And the group down at the bottom is F. We also have different numbers which are used. So those these colored squares represent the different shapes of the orbitals, but then the energy levels are also present here too. So for the s orbital, it starts at 1. For the p orbital, it starts at 2. For the d orbital, it starts at 3. And for the f orbital, it starts at 4. So finding the electron configuration, we can basically just go left to right, starting at hydrogen, working our way down until we find the element that we're trying to locate. So for example, the first one we're trying to find is sulfur. So we can find our electron configuration by starting at hydrogen and working our way across left to right, top to bottom, until we reach sulfur. So we're starting in the 1s section, and we go 1s and we cross 2 boxes. So we would write for sulfur 1s2. Then we move down to the next row. We're in the 2s section. We go through 2 spaces, so 2s2, and then we, going left to right, jump across here. Now we're in 2p, 1, 2, 3, 4, 5, 6. So we'd write 2p6. Then we jump down to 3, 3s2. Oops. And then across to 3p, 1, 2, 3, 4. And we stop once we've landed on the element that we want. So we don't keep going after that. We land on that element, and then that gives us our electron configuration. Now we can do this for any element on the periodic table. So suppose we had one that was further down. Let's say we're looking for tungsten instead. So we would start in the same location. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. But now this time we run into the D block. So we see that the number starts at 3. So we write 3D and we cross through 10 spaces. Then we're back to P, 4P6. Then we come down to 5S, 5S2. We're back to D again, so it's 4D, 4D10. Then we're at 5P6. And then we get to 6S, 6S2. And this is where it gets tricky. So on our periodic tables, there's this little star here. That means that once we get here, we need to move down to the lanthanides. We need to use this F block here before we can come up to the D block. And so we had 6s2. Now we jump to 4f. And we go through 14 spaces before jumping back up to the D block. So that would be 5D. And then 1, 2, 3, 4 to get us to tungsten. Okay, so one thing we can do to make our lives a little bit easier is to create the condensed electron configuration. So when we write the condensed electron configuration, we can use the fact that the noble gases have a complete set of electrons every time because they're at the very end of the row. And so we can use them kind of as a waypoint that allows us to say that everything before that is filled and that it's the same every time. So let's look at an example. Let's find cadmium, Cd, and we're going to write the electron configuration for cadmium, but we're going to do it in the condensed way. So to write the electron configuration condensed, we start by going up one row and all the way to the end, and we wind up with Kr, which is a noble gas. So we write that in brackets, Kr. And then we start at the row that cadmium is in, which is 1, 2, 3, 4, 5s. And we cross through 2 spaces. Then we'll be in 4D. And we cross through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to land on cadmium. We can do this with any element. So for example, radium is right here. So again, we just go up one row all the way to the end. We find our noble gas. So we put that in brackets. And then we start at the row that radium is in, which is 7. So we have 7s, 1, 2. And that is a condensed electron configuration. So one thing we'll do this year that we didn't do last year is orbital diagrams. We can put our electron configurations into an orbital diagram or vice versa. But basically, we show that each orbital can hold only 2 electrons that spin in opposite directions. And we do that using arrows that are in opposite directions. When we add the electrons into the orbital diagrams, we have to remember that we only fill them one at a time. We don't pair them up until each orbital has 1 electron, and then we go back and refill to pair them up. In an orbital diagram, we show the spin of each electron in the different orbitals. And so we do that with arrows. And so it's basically like an electron configuration, but it gives us this extra information of the spin of the electrons. And it also shows us whether there are paired or unpaired electrons in each orbital. So let's look at some examples. So again, let's take a look at sulfur. So we just did the electron configuration for sulfur. We started at 1s, and there were 2 electrons in 1s. So we have one that's spinning up and one that's spinning down. You can think of that as clockwise and counterclockwise, positive or negative, whatever, but they just have to be opposite spins. So then next we go to 2s. We also had 2. Then to 2p, we had 6, 2p6, so it was 1, 2, 3, 4, 5, 6. I fill them in that way because we need to only have 1 electron in each orbital before we can go back and pair them up. So then we get to 3s, 3s2, and then S is in the 3p orbital. Sulfur is in the 3p orbital. So it was 1, 2, 3, 4. So we put 4 electrons here. 1, 2, 3, 4. It's important that you fill them this way by doing one at a time before pairing, or else you'll end up with a different situation. Like you'd have, if we just paired them up right away, it would look like this, which is not correct. So we need to fill them in one at a time to see that there's 2 unpaired electrons in sulfur. Okay, so let's take a look at another example. Let's look at cadmium, which we also did the electron configuration for earlier. For cadmium, we know we're filled up until the 5s. So we can go ahead and fill these in because our electron configuration that we did was condensed. We saw that the 5s is where we started counting for cadmium. Before that, it was just the noble gas, which is completely filled. So I'm just going to fill these in. 5s, yep, okay. So at 5s, we had 5s2, and then we were in 4d, which wound up being 4d10. So to fill that in, again, we start 1, 2, 3, 4, 5, fill them up individually first, 6, 7, 8, 9, 10. Now in this case, they all wound up to be paired, but that's not always the case. And so it's really important that you go through with these ones that have multiple spaces and fill them up one at a time.